Hi guys, welcome to section 1.2 where we're going to continue doing transformations, but we're going to specifically do the absolute value function. So let's quickly take a little look back at the graph of our parent absolute value function. I'm going to fill out this table of values here on the left as we did in the last lesson relatively quickly. Remember that when we plug in our x value into our function f of x equals the absolute value of x, what we are doing is taking the absolute value of that number. So as we know, the absolute value of -3 is 3, of -2 is 2, -1 is 1, and so on and so forth. And our values repeat themselves after we reach the x value of 0. And then that gives us a bunch of ordered pairs that we can plot that are on this graph. So these are the points I'm going to plot on my graph here. These are not the only points on my absolute value function. These are just some that are going to help me get an idea of what the graph looks like. So I'll plot the point -3, +3, -2, +2, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3. Now, of course, we see the pattern. We could continue this all the way through our graph. And of course, we would also want to take our straight edge and draw this function for all values on our graph that we can see. Okay, so we have some important pieces of this graph. The first one, we did talk about the vertex the other day. The vertex sits at 0, 0. That's going to be a very important point for us when we start translating this graph, moving it around. Also, some terms that we should revisit that we should know about are domain and range. Remember that domain of a function includes all the x values for which the function is defined. So all x values for which the function is defined. Now that's kind of a mathy definition. Another way to think of it is what x values can you put into this function? And in this particular function, what x values can you take the absolute value of? Well, if you think about it, every number on the number line has an absolute value. It has a distance from 0. So we can put any x value we want into our function and we will get out a y value, which is our range. This is just our set of outputs after we put those domain values in, which are also our y values. Okay, and you can also see domain and range from the graph. So we're going to look at that. As we see, our graph has arrows at each end, which means it goes on forever in each direction, and it's a continuous graph. There are no holes, there are no jumps. That means that it covers every single x value on that graph. So if we're talking about that, we might describe the domain in a few different ways. We could say all real x values. Some of you might use the symbol for the set of all real numbers, or you can do an inequality. Negative infinity is less than x, which is less than positive infinity. So I just basically gave you 3 different ways to write it. You can choose how you would like to. The range, however, we're going to write it as an inequality. If you can see, the lowest point on our graph is right here at 0, 0. So we have no y values in negative territory. So our entire graph, this blue part, lies above this point at our vertex, which is at a y value of 0. So our range is y is greater than or equal to 0, which makes sense because when we're taking the absolute value of numbers, the lowest number we'll ever get is 0 because the absolute value of 0 is 0. All other absolute values are positive. Okay, we're going to move on to translating, our first transformation, but our learning target is encompassing all of our transformations. I can identify the transformations applied to an absolute value function from its graph and its equation. Okay, so translating. We represent translations in a function by adding or subtracting, and I underline those, you highlight if you would like, the parameters h and k. Okay, Okay, the parameters h and k in the general equation g of x when it's a transformation of the graph of function f of x. So this is in general, g of x equals f of x minus h plus k. So we can use this form for any type of function, but we are specifically talking about absolute value today. So if we were to rewrite this general equation for if our f of x is the absolute value of x, we would write this as g of x equals absolute value of x minus h plus k. So we don't have that letter f in our function anymore because we said, hey, f is absolute value. So we're going to write this x minus h plus k in the absolute value function. So this is what we're going to be seeing today. Okay, we did a little exploration in the last lesson, so I hope that this is familiar. If we are going to move right or left, that's a horizontal translation, and that is from our h value. And this happens inside the function. So because this is an absolute value function, it happens inside the absolute value bars. It changes the x coordinate because it's horizontal. And if we see g of x equals the absolute value of x plus h, we are going to move left. And if we have the absolute value of x minus h, we are going to move right. And you may be thinking, hold up, that seems a little backwards. Well, guess what it is? We have to think opposite when we are moving horizontally because of this x minus h sign. So whenever we put something in for h, we're always going to put that negative in front of it, which changes its sign. So always think opposite with your horizontal translations. Vertical is on the outside of the function. Our k value comes after the function. So it's not inside the absolute value bars. It's outside of it. It could actually be in front of it. But we generally like to write it at the back. It changes the y coordinate because it's vertical. If we have the absolute value of x and we add k, that will move up. And if we subtract k, that will move down. So go ahead and keep those boxes in your sight when we do these examples. Given each equation, identify the translations applied to the parent graph of the absolute value function. Then identify the vertex and domain and range. Ooh, let's see here. Letter A, g of x equals x plus 4, absolute value of x plus 4, then minus 1. So this x plus 4 is inside. We always think opposite on the inside. So my h is actually negative 4. My k is negative 1. So I am moving left 4, down 1. Now remember our vertex starts at 0, 0. And if I'm going to move that left 4, down 1, it's going to just move to negative 4, negative 1. I want to think about that. Left 4, down 1, about right there. It's still going to be opening upward. So just a little hint with absolute value. Your domain is always all real numbers. So I'm just going to write this every time. But my range, now because my vertex has a y value of negative 1, my whole graph is above that value. So y is greater than or equal to negative 1. All right, I'm going to do B. B doesn't have an h value in it, which means h is 0. So I haven't moved right or left. But on the outside, it has a k value of 5. So all I did was go up 5, which means my vertex is at the point 0, 5. And so if I moved up 5, here's my graph. My whole graph is still above the vertex or equal to. So my range is y is greater than or equal to 5. And I hope you remember your domain for absolute value is always going to be all real numbers. The last one, I have g of x equals the absolute value of x minus 2, then plus 3. So remember, think opposite on the inside. This is actually an h value of 2 and then a k value of 3, which means I am moving right 2, up 3, which makes my vertex 2, 3. So very quickly, because my vertex is at the point 2, 3, but my graph is still opening upwards, my range is y is greater than or equal to my y coordinate 3. That's your range. Your domain is still all real numbers.